Now, having successfully constructed a few stochastic processes like random walks and the Poisson process, it's time to start a full development of Markov processes. The starting point is the Markov property that we developed as a consequence of our random dynamics model in lecture 34.2. We start with a filtered probability space, so that's a regular old probability space, together with a filtration of sigma fields inside the base sigma field, filtered over a time set, which will usually either be the natural numbers or the real numbers, always starting at some starting time, which we'll call 0. An adapted stochastic process, which remember means that at each time xt is measurable with respect to the filtration at time t, is said to satisfy the Markov property if, for all bounded functions of the state space, if we condition that function of the process on the filtration at an earlier time, that's the same as conditioning that function of the process at just that earlier instant. That is, conditioning this on the sigma field up to time s is the same as conditioning on just the random variable s. Now, this is equivalent to stating that the conditional expectation of a function of the process on the sigma field up to time s is some bounded function of the process at time s. To see that for the forward direction, we simply note that the Markov property tells us that this is the same as this. Of course, conditioning on xs gives us something that is xs measurable, and by the Dinkin representation, anything that is xs measurable is a function of xs. For the reverse direction, we assume that we have this form here, conditioning a function of the process at time t on the sigma field up to time s is a function of the process at time s. Well, if it's a function of the process at time s, then if I further condition on the random variable at time s, that won't change the value. And now we use our assumption that that function of xs is actually the conditional expectation of the function of the process at time t on the earlier sigma field xs. But now we can use the tower property. Our process is adapted, and that means exactly that this sigma field is contained in here. And so by the tower property of conditional expectations, this double conditioning is just the same as conditioning on the smaller of those two sigma fields. And there we have it. That's the definition of the conditional expectation of f at xt given xs, verifying the Markov property. Now, when we derived the Markov property from our random dynamics model, it was with respect to the sigma field generated by the stochastic process. Let's give that some notation. Given a stochastic process, the sigma field that it generates, fxt, is the minimal sigma field with respect to which all of the variables xs up to time t are measurable. In this language, saying that a random process x is adapted is the same thing as saying that the sigma field that it generates up to time t is contained in the filtration sigma field at time t for all t. Now, this brings up a technical point because the Markov property with respect to this sigma field isn't the same as the Markov property with respect to a sigma field that we started with. That is this. Here we are conditioning on a larger sigma field than this, potentially strictly larger, and so this is simply a different statement than this one. They are related, however. This one is actually stronger. If this general Markov property holds, then the Markov property for that process relative to the sigma field that it generates will hold. And that again is just going to follow from the tower property for conditional expectations. If I take the conditional expectation of f at xt given the filtration generated by the process at time s, well, then I can use the tower property to express this as conditioning on that fxs and conditioning on the full sigma field fs That's because our process is adapted, and therefore this is contained in this. Now, if this more general Markov property holds here, then I can express this inside conditioning as just conditioning on the random variable at time s. And now I can use the tower property again, since this is contained in here as the process is adapted. And this is just conditioning on sigma of xs. And that gives me this weaker Markov property with respect to the filtration generated by the process itself. Now, in practice, we will often be dealing with this as our filtration, but in cases where we have more than one stochastic process around and we have a filtration hanging around from the start, this is actually a stronger Markov property. If we say that a process satisfies the Markov property, this is the weakest thing that we could possibly mean, but we might mean something stronger if there is a filtration around already. Now, another clarification based on how we derived the Markov property. The Markov property from lecture 34.2 was for a discrete stochastic process, and so it was in discrete time. In discrete time, in general, we can simplify the statement of the Markov property. The Markov property says this for discrete time. That is, if k is a discrete time less than or equal to n, then I get the conditioning on fk as conditioning on xk. But we can simplify that and state it only for the case where k is equal to n minus 1. That is, I can just state it for the one-step conditioning, and that is sufficient to derive the general Markov property. Proving that is a straightforward induction. So the base case of this induction is where k is equal to n, and of course in that case here, this just holds because both sides are equal to f at xn. Now we're going to proceed by induction for fixed k incrementing n. So we'll assume that we've shown this to be true for fixed k up to level n, and we'd like to show that it's true at level n plus 1. We're going to do so by using the one-step Markov property, which we're assuming here. So what do we know about conditioning at time n plus 1? What we know is that conditioning on the sigma field up to time n, we get the same thing as conditioning on the random variable at time n, which, as we showed on the last slide, is just, therefore, a function of xn. Therefore, if I try to condition on the sigma field at time k, this function of xn plus 1, well, I can use the tower property because fk is contained in fn, being a filtration and all. Now we just finished showing that this inside here is a function of xn. So this gives me conditional expectation onto fk of f at xn. Now I'm set up to use the strong inductive hypothesis here. We showed that at stage n, I can reduce this to conditioning on the random variable xk instead of the sigma field xk. So therefore we get that this is equal to the conditional expectation of capital F at xn given just xk. Now inside, this is just the conditional expectation onto fn of this function of the process at time n plus 1. But the sigma field generated by xk is contained in fk, and fk is contained in fn. And so by the tower property, this double conditioning is just the same as conditioning on the sigma field generated by xk alone, and that gives us the statement we want. So we've shown by induction that this holds, concluding the proof. Now, what does the Markov property really mean? It's a statement about the present versus the past, but actually, it also can be made into a statement about the future. Given a stochastic process, the future sigma field that it generates, fx at greater than or equal to s, is defined to be the minimal sigma field with respect to which xt is measurable for all t bigger than or equal to s. It's complementary in time to the filtration generated by the process. This is not a filtration in S, it is a reverse filtration. If I increase S, then I decrease this sigma field. The Markov property can be reformulated into what appears to be a stronger statement that not only does the present not depend on the past except through this instant, but also the whole future doesn't depend on the past except through this instant. So here's the formal statement of that. Suppose we have a process which satisfies the Markov property, then if I take any bounded random variable measurable with respect to the future sigma field of that process, the conditional expectation of that random variable on the sigma field up to time s is the same as the conditional expectation of that random variable onto the variable xs. The future only depends on the past through the present. We're going to take a couple of slides to prove this. Before we get started, let's see if we can understand what kinds of random variables are represented here. A good example of a future measurable random variable can be constructed as follows. If I take a bunch of one variable measurable functions, g0, g1, up to gn, that are all bounded measurable functions on the state space, and I take a sequence of times, which I'll usually start with t0 being at the time s, t1 up to tn, then I could take y to be the product g0 of x at t0, g1 of x at t1, up to gnx of tn. So since those are all bounded functions, this will be a bounded function. And since each one of them is measurable with respect to one of these sigma fields for a fixed t, where all the t's are bigger than or equal to s, this is a bounded measurable random variable with respect to the future sigma field, the future of s. And in fact, we're going to prove this proposition by first proving it for these kinds of future random variables and using Dinkin to show that that's good enough. So in order to apply Dinkin's multiplicative systems theorem here, I need to show that this collection of random variables forms a multiplicative system and that the sigma field it generates is this full sigma field here. So that's our lemma right here. Now, to see that it's a multiplicative system is just from the definition. It's defined to be a set of products of things, and so if I take two of these and take their product, I get another product of functions of the process at times in the future of s. So the key here is to show that the sigma field generated by this multiplicative system is the future of time s for the process. Well, if A is an event in the future sigma field of time s, which remember means the sigma field generated by all the random variables xt with t bigger than or equal to s, that means that A has the form, the preimage under xt of some set B in the range, and some time t in the future. I want to be able to represent that as something in sigma of m. Well, I can do that just by writing this as the indicator of B composed with xt preimage on 1. Because the indicator of B takes value 1 exactly on B. So that is in the sigma field generated by M, since this is a function in M. So that shows us that we have this containment here. For the reverse, we need to show that any event A in this sigma field is in the future sigma field. Well, if it's in sigma of M, that means that A is the preimage under some random variable y of some set E, where y is in the multiplicative system, and E is a Borel set in the real line. But our multiplicative system here consists of functions of the process at some times that are in the future of s. That means that y will be measurable with respect to the sigma field generated by all the times in the future of s, and therefore for any Borel set E, this preimage will indeed be in this sigma field. So that shows the forward containment and shows that sigma of m is equal to the future sigma field as desired. Okay, so now our goal was to prove the proposition, that is, that for a Markov process, the future depends on the past only through the present, by using Dinkin's multiplicative systems theorem. We've got a multiplicative system, and now we need to find a subspace H that contains it, that we will show is the full set of functions that we want. So here is that subspace H. It's the set of all future measurable random variables for which the desired property holds. The conditional expectation of that random variable given the past up to time s is the same as the conditional expectation of that random variable just given xs. Well, we're going to show that that H is a subspace of the space of all bounded measurable functions, future measurable, that it contains one, and that it's closed under bounded convergence in order to use Dinkin's multiplicative systems theorem. So to see that it's a subspace, that's just a matter of noting linearity of conditional expectation for any subsigma field G, where on the left we're using it with G is equal to Fs, and on the right we're using it with G is equal to the sigma field generated by Xs. So since both of these are linear in the y variable, it follows that H is a subspace. To see that it contains the constant function 1, that's just because on both sides of the desired equality, the conditional expectation of 1 is just 1. And so we just need to see that this set H is closed under bounded convergence. In other words, we need to see that if yn converges to y boundedly, and yn is in H, then y will also be in H. Well, if yn is in H, that means that this equality holds for each term in that sequence. And yn converges to y pointwise and boundedly, we'd like to see that we get equality here as well. If we didn't have conditioning here, this would just be an immediate application of the dominated convergence theorem. Well, with conditioning there, it's still an immediate application of the conditional dominated convergence theorem. And that concludes the proof of this lemma. So that sets us up nicely to prove the proposition, which I've restated here. Given a process with the Markov property, if I take any future measurable random variable and condition it on the past, that's the same as conditioning it on the present. So in other words, what we want to show is that that subspace from the last lemma is actually all future measurable bounded random variables. And we showed that M, the set of products of one variable future measurable functions of the process at future times, is a multiplicative system which generates this as a sigma field. And so, by Dinkin's multiplicative systems theorem, all we need to do is show that M is contained in H to conclude that H is actually all of this. So let's take a y in M. So it has this form for some functions g0 through gn and some times in the future of t0, which is s. And we want to show that if we condition that y on fs, we just get the conditioning of y on xs. Well, we use the tower property once again. Let's further condition on time tn-1. Since tn-1 is in the future of s, fs is contained in this sigma field. Now let's look at that inside conditioning on the larger sigma field f at time tn-1. Y is this product here. And except for the last term, it's a function of times t0, t1 up to tn-1 that are all less than or equal to tn-1. So we can use the product rule to pull those measurable functions out. g0 of x t0, g1 of x t1, up to gn-1 of x tn-1. And what we're left with is just to condition on tn-1 of the last term, gn of xtn. So let's call that function there h, and it is a function of xtn-1 by the Markov property. So that means that this overall conditioning here is just conditioning on fs of that product times h of xtn-1. Now let's rename this product of two functions at time tn-1 as just gn-1 tilde of xtn-1. And so we have reduced this conditioning of a product of n plus 1 things down to a product of n things only up to time tn-1. Now we rinse, lather, repeat, And by induction, we're eventually going to find that this conditioning is the same thing as conditioning on just a function of the process at time 0. Time 0 is s, and so that's just f at xs. And therefore, conditioning y on fs gives a function of xs, and following the same argument we made at the beginning of this lecture, this is the conditional expectation of f at xs. Given xs, since this is xs measurable, but f at xs is, back through this chain of equalities, conditioning y on the sigma field at time s, and the sigma field at time s contains the sigma field generated by xs, and so by the Tower property, this will be the conditional expectation of y given xs. And so that shows that this equality, which is the equality we were looking for, holds for all y in M. That means that M is contained in H, and that means, by Dinkin's multiplicative systems theorem, that H actually contains all bounded measurable functions, that is, measurable with respect to the sigma field generated by M, which, as we showed, is the full future sigma field, and that concludes the proof of this proposition. So that's another way to state the Markov property. The future depends on the past only through the present. Now, if we're talking about dependence there, that suggests that we might want to phrase things in terms of independence. And we can do that again, but we need slightly new language. We need to talk about conditional independence. Given a probability space, omega fp, and 3 subsigma fields, A, B, and G, we say that the 2 subsigma fields A and B are conditionally independent, given the sigma field G, if this conditional version of the independence statement holds true. That is, the conditional probability of A intersect B given G, which is a random variable, is almost surely equal to the conditional probability of A given G times the conditional probability of B given G for all events A in A and B in B. Remember that this conditional probability here, this random variable, is the conditional expectation of the indicator of A intersect B given G, and the indicator of A intersect B is the same as the indicator of A times the indicator of B. And so we can see through usual Dinkin multiplicative system theorem type arguments that this is going to be equivalent to the functional form here, that if I have any bounded measurable function of A and any bounded measurable function of B, the conditional expectation of their product given G is the product of their conditional expectations given G, almost surely. That's the definition of conditional independence. Now, conditional independence probably sounds, the way it's phrased, like, well, they're not independent, but at least they're conditionally independent. That's the wrong intuition. Conditional independence doesn't have anything to do with regular independence. In fact, random variables can be independent, but conditionally dependent. Let's look at an example. First, let's rephrase conditional independence in terms of the non-functional form. You can check easily that this property here means that if C is any event in G with positive probability, the conditional probability of A intersect B given C is the product of the conditional probabilities of A and B, each given C. And that's an exercise for you to work out. In other words, conditional independence given G implies that if I select any positive probability event in G, the conditional probability measure given C makes these 2 sigma fields independent. So here's a quick example. Suppose x and y are independent random variables, which take values 1 and 2, each with equal probability. I have 2 fair coins with a 1 on one side and a 2 on the other side. I'm going to condition on the event that x equals y. Of course, the event that x equals y has probability 1/4 plus 1/4, or 1/2, so positive probability. Because of the identical distribution of the 2 random variables, the conditional expectation of x given x equals y is the same as the conditional expectation of y given that x equals y, and in this discrete setting, that's just the expectation of x times the indicator that x equals y divided by the probability that x equals y. So on the event x equals y, x can take 2 values, 1 and 2, and it takes those on this event, each with probability 1/4, and so we get this calculation here, which tells us that this conditional expectation is 3/2. I can similarly work out the conditional expectation of xy given the event that x equals y, and I get 5/4. The problem is that 5/4 is not equal to 3/2 times 3/2. And so, although these two random variables are independent, they are not conditionally independent given the event that x equals y. That's just something to bear in mind as we go forward talking about conditional independence. So now that we have this definition under our belts, let's finally rephrase the Markov property one more time in a somewhat poetic way. The Markov property says that conditioned on the present, the past and the future are independent. Let's be precise. We start out with a filtered probability space and an adapted stochastic process on it. Then that process satisfies the Markov property if and only if for each time S, the past sigma field of S in the filtration and the future sigma field of S generated by the process are conditionally independent given the sigma field generated by xs at time s. Since our process is adapted, the sigma field up to time s contains the sigma field generated by xt up to time s, and the future sigma field is the sigma field generated by xt for t bigger than or equal to s. So this really does say that all the information that the process gives us in the past and all the information the process gives us in the future, those two sigma fields are independent given this sigma field under conditioning. So let's prove this. First, let's suppose that the Markov property holds. Then if I take any bounded measurable function of the past, z, and any bounded measurable function of the future, y, and take the conditional expectation of z times y given fs, well, z is measurable with respect to fs, and so by the product rule, this is z times the conditional expectation of y given fs. And by the proposition we just proved, that conditional expectation, since y is future s measurable, is the same as the conditional expectation of y given just xs. Therefore, if I further condition this on the sigma field just generated by s, that's the conditional expectation given xs of z times the conditional expectation given xs of y. And now I'm going to use the product rule again. This time, this is the random variable that isn't necessarily measurable here, but this one is. And so I can pull this one out. But on the other hand, by the tower property, since this sigma field is contained in this one, this is equal to the conditional expectation given just xs of z times y. And there is our forward statement. We get that for all bounded past measurable and bounded future measurable functions, conditioned on xs, the expectation of zy is the product of the expectations of z and y. That tells us that we have conditional independence given xs. That's the forward direction, and the reverse direction is on your homework. From here, we're going to move on to talk about Markov processes. One would hope that a Markov process is just a process satisfying the Markov property, but it turns out that, at least in the continuous time case, to avoid some measure-theoretic problems, we need to make a slightly stronger statement than that. And in order to do so, I'm going to briefly revisit probability kernels and regular conditional distributions to get our notation straight before proceeding.